It's another math day here with teacher Jenny. Join me for another topic, and this time we're going to talk about limits of transcendental functions. This time we are going to talk about special cases of the limits of transcendental functions, especially on the trigonometric functions. So we have different cases here, one of which, once you've got this format of your function, if you've got the limit of x over sine of x as your x approaches 0, notice that upon substitution, this will lead to a 0 over sine 0. Now for the sine 0, if this will be our 0 on the as the angle on the Cartesian plane, this would simply mean that the coordinate here will be a 1 and 0. Our y there is a 0. This would lead to a 0 over 0, which is an indeterminate form. And same goes with the second one. So since this would lead to us to an indeterminate form, then we have our theorem for that one, that once we've got this format, this will be automatically equal to a 1. And of course, our main goal here is for us to check whether this one here and the angle here are alike or they are the same. If that will be the case, then that is equal to 1. Same goes with this one here. Now for the third one, we have 1 minus cosine x over x. Getting the limit of that as x approaches 0, this would lead to a 1 minus cosine 0 over a 0. For the cosine 0, our x here has 1, so that means to say, substituting the value of cosine 0, which is 1 minus 1 over 0, this is still leading to a 0 over 0 or indeterminate form. So that is why we have a theorem here in which once we have this format in which our angle here is equal to the value here, automatic that will be equal to a 0. So lastly, we have the limit of e to the power of x minus 1 over x as your x approaches to 0. Because if we got e to the power of 0 here minus 1 over 0, this would lead to an e to the power of 0 is 1 minus 1 over 0. This will be now a 0 over 0 still. That would lead to an indeterminate form. So that is why once you encounter this one in which you've got your exponent on e similar to the one at the bottom part, then you've got this one as equal to 1. So let's try to apply those on our example here. So we have the limit of sine 3t over t as your t approaches 0. So again, once you try to substitute your approach value to your t here, this would lead to an indeterminate form. So that is why we need to transform this one into equal to this one. And doing that one, we may try to do the manipulation here. Similar with the limits of the algebraic functions, once you have an indeterminate form, we do the algebraic manipulation. So this is the same idea. Only that what we're manipulating here is this angle here, and so with the denominator here. To make it the same, we lack 3 here. And in order for us to have the 3 here, we will be multiplying the top and the bottom part with a 3 to make it a 3t. So this will be now the limit of 3 sine 3t over 3t as your t approaches a 0. So since we have a multiple here, a constant multiple, and according to the law of theorem, once we have the constant multiple, we are to get that out from the limit function. So we have here 3, and then we've got the limit of sine 3t over 3t as your t approaches 0. This one becomes 1, so we've got that as 3 times 1, in which that is equal to a 3. Next, we have here a limit of x over sine 4x as your x approaches to a 0. So again, once you try to substitute that one with a 0 on x here, this would lead to an indeterminate form. So we do the manipulation. What is missing at the top that will make that one equivalent to the angle here? We don't have a 4, so we are going to multiply this with a 4, and so with at the bottom part, and then we try to simplify. This is now limit of 4x over 4 sine 4x as your x approaches a 0. Then we are going to get the constant multiple out. This will be now getting out this 4 here, since this is on the denominator, and which means, let me just try to separate that. This will be equivalent to 1 over 4 times 4x over sine 4x as your x approaches a 0. Taking out the constant multiple, we have 1/4, and then we have the limit of 4x over sine 4x as your x approaches a 0. This would lead to a 1, so we have 1/4 times 1, that will be a 1/4. We have limit of 8t squared over 10 squared 4t as your t approaches a 0. So once again, if we try to plug in the approach value there, that would lead to an indeterminate form. So all we have to do is to simply do the manipulation here, and since we cannot find a special case in which the tangent is involved with, so we are going to transform the tangent into basic trigonometric function as cosine and sine. So we've got here a limit of 8t squared over our tangent squared 4t. We can just transform that one into sine squared 4t over cosine squared 4t as your t approaches a 0. So out from there, we can just simply simplify this one. Since the denominator is a fraction, we simplify that one by getting the reciprocal of that and multiplying that one to the numerator. So we have limit of 8t squared as the numerator times the reciprocal of this. We have that as cosine squared 4t over sine squared 4t. And then we are going to simplify that. We can have their limit of 8t squared. By the way, since we have the sine squared 4t in there, we can just go ahead and group that one with the one which got the t at the top. So we can simply have it. Anyways, I'll just continue with what am I supposed to do a while ago, so that you will not be confused. So we have over sine squared 4t as your t approaches a 0. And then after this one, notice that our cosine squared 4t is at the top, but we don't have a 1 minus in there, so we don't need to be bothered by that cosine squared 4t. What we are more concerned of is we have the sine squared 4t here, and remembering the theorem on the special cases, we have the sine squared 4t there, given that 4t is also at the top. So out from there, we can just simply factor out 4t here. So this will now be like this. We have the limit of 4t over sine squared 4t, but notice that we have another sign here. This is actually written as like this. So let me just return that one and break that sine squared 4t first, so that you will not be confused as well. We have our 8t squared cosine squared 4t, breaking up our sine squared 4t at the bottom part. We have sine 4t times sine 4t, because our theorem there is only with a single sign. We don't have it squared in there. So continuing, we have that one, the sine 4t. We can partner that one at the top with a 4t. So this will be now limit of a 4t will be broken. We need to break the 80 squared there, having 4t, and the remaining there is with a 2t. And then we have our cosine squared 4t over the sine 4t times the sine 4t. Now the reason for the breaking or factoring out our 80 squared there is we will be utilizing the 4t and partner that one with the sine 4t at the bottom part. So we have here limit of 4t over sine 4t times we have our 2t over, we can partner that one as well as with our sine 4t. And then we have times cosine squared 4t. So looking at that one, we have now already pictured out as to what will be the value of this one once we get the limit of that one that's equal to a 1. But for this one, we need to have it completed, meaning we have to find a number that will make this 2t equal to 4t. So we need to multiply that one with 2 over 2. Now simplifying that one, let me just get this one out. Separate each of the limit there according to the factors. Limit of 4t over sine 4t as your t approaches a 0 times, we have 2t times 2, that's a 4t. And then I'm going to write my limit in there. We have 4t over 2 sine 4t as your t approaches a 0. Another limit here on cosine squared for t as your t approaches a 0. So this one will become a 1 here times getting out or getting the 2 out. Since this is on the denominator, we have that also written on the denominator. That means we have a 1 at the top, and then we've got the limit of 4t over sine 4t as your t approaches a 0. And then we have here times the limit of cosine squared 4t as your t approaches a 0. So we have 1 times 1/2, and then we have this as 1, and then times the limit of cosine squared 4t. 1 times 1/2 is 1/2 still, and then we have the limit of cosine squared 4t. We can simply substitute our t there as your t approaches, our t value as our t approaches 0. So we have 1/2 times cosine of cosine squared times cosine squared 4 times a 0. So this is similar to having 1/2 and then cosine squared of a 0. Cosine squared of a 0 or cosine 0 squared, this is equal to, I can rewrite this one as cosine 0 times cosine 0. So if you try to look at the Cartesian plane, this is 0. Coordinate of that one under the unit circle is 1, 0. Our cosine is always on the x, so we have that one as 1. This is similar to writing 1/2 times 1 times 1, which is equal to 1/2. So this is our limit for that particular function. Let us now have this one here. So we have limit of sine squared 5 theta over theta squared as your theta approaches a 0. So once again, once you try to substitute that one, that would lead to an indeterminate form. So we do the manipulation here. Since we wanted to have this one similar to this, But looking at this, we have a square here. So let's try to expand that one. So we have now the limit of the sine squared phi theta there. This is similar to having a sine squared phi theta times, the sine without the square already, because I wanted to have that one separated, so that it will be a lot easier for me to manipulate that one. So we have here sine phi theta, and then over our, we also have to break this one because that is on square. So I can write that one as a theta times theta, and then we have a theta approaches a 0. So this will be equal to, let's try to break them apart. We have the limit of sine phi theta over theta, so times sine phi theta over a theta here as our theta approaches a 0. So out from here, we are now ready to identify as to what will make this denominator equal to the angle here. So we can just simply multiply this by 5, and so with this one. And so with the other factor, we can multiply that one with a 5. So this will be now a limit of 5 times sine theta over 5 theta times 5 sine theta over 5 theta as your theta approaches a 0. So out from there, we can take out the constant multiple, so we can take out 5, and another 5 here will be taken out, so this will be multiplied, and then we have the limit of sine theta over a 5 theta, sorry, that should be without 5 theta, and then times the limit of sine phi theta over a 5 theta as your theta approaches a 0, and same with this one here. So 5 times 5, that is 25, and then sine of this, limit of this, that's equal to a 1 times the limit of that one, that's also equal to a 1, and this is now equal to 25. So that is how you are going to get the limit of the special cases, which is particularly we're concentrating on the sine sine of an angle here over an angle. Sine, most likely the special case of the sine. So once again, this is your teacher Jenny saying, practice and practice, and one day you'll get perfect.